Let's now look at what happens when we perform a sequence of transformations. Will the order matter? As we know it will. And let us see in an example exactly how the order in which we perform transformations results in different pictures. Say, for example, we perform two vertical transformations. We vertically shift by 3 units, and then after that we vertically stretch by a factor of 2. What kind of graph will that be? Well, a vertical shift upward by 3 results in the graph f plus 3. And a vertical stretch by a factor of 2 results in twice whatever we began with. Is it the same as doing these operations in reversed order? Let's think. In the reversed order, we will first stretch by a factor of 2. And then second, we will vertically shift upward by 3 units. In this case, we produce a different function. Vertical stretch by a factor of 2 results in twice f of x, and a vertical shift by a factor of 3 results in adding a 3 to this. Of course, these two are not equal, because this here on the left is 2f of x plus 6. And if you think about what happened, you can see immediately that when you first shift and then stretch, you also stretch the shift. We were actually shifting by 3, but when you apply a stretch, the shift is now by 6, not by 3. Whereas this does not happen when we stretch first and then shift. In principle, you can go either way, but you have to be aware that the order of shifting and stretching is very much important. Now, let's think about horizontal transformations. Let's say we want to produce the graph of function g, which is f of 2x plus 3. Suppose we know that f at 7 is 12. So the graph of f passes through the point 7, 12. The question is, what input of g would produce the value 12? For what x will g of x be equal to 12? Well, because g of x is f at 2x plus 3, we need 2x plus 3 be 7, because 7 is where f is 12. Now, when we look at this equation, 2x plus 3 equals 7, and think how we solve it for x, we see that we first subtract 3, which produces a horizontal shift, and then we divide by 2, correct? We have 2x plus 3 equals 7. Now we have 2x equals 7 minus 3, and that's a shift. That is a horizontal shift. And when you divide by 2, that is a horizontal compression or stretching. Depends on how you look at it. So when you look at it this way, you first perform a horizontal shift and then a horizontal compression. This actually is not the preferred way of doing this because it's much easier to horizontally stretch before shifting. There's an example later that will explain why this is the preferable way. Now let's see in general how we work with the graph of f of bx plus p where b and p are constants. The trick is to factor out b. When you factor out b, you have in parentheses x plus p over b. Of course, here we assume that b is not 0. And suppose f at alpha equals beta. The question is again, when input of f is alpha, the output is beta. For what input of g will the output be beta? Well, we need to equate the argument of f, b times x plus p over b, to whatever number alpha that produces output beta. Just like above, we equated 2x plus 3 to 7, because f at 7 produced 12. And when you look at it this way, and think how you would be solving this equation for x, you are first dividing by b, which gives you a compression or a stretch. And then you subtract b over p, which gives you a horizontal shift. So you see, in the previous example, we were shifting first horizontally and then compressing horizontally. When you do it this way, you stretch first and then shift. So what would that mean for this particular example of f at 7 being 12 and g of x being f at 2x plus 3? Well, we factor out 2. So in parentheses, we have x plus 3 halves. And when we equate 2x plus 3, written in this form, to 7, we're first dividing by 2, then subtracting 3 halves. So we're first performing a horizontal compression, then a horizontal shift. In principle, you can do it either way. But again, you have to be aware of what you are doing. I recommend compressing or stretching first and then shifting. Because again, if you're first shifting and then stretching, you may also stretch the shift, which is not something that you may want. In principle, you can go either way. If you have your function g written this way, a times f of b times x plus c, then the order of operations is this. You stretch or compress horizontally according to what b is, and we know what that means. If b is greater than 1, you stretch. If b is between 0 and 1, you compress with a factor of 1 over b. If b is negative, you also reflect about the y-axis. Then you take care of c. We need to shift horizontally. By absolute value of c, For positive c, we shift to the left. For negative c, we shift to the right. And then finally, we take care of this factor a. And again, if a is greater than 1, we stretch vertically. If a is between 0 and 1, we compress vertically with a factor of 1 over a. And if a is negative, on top of that, we also perform a reflection about the x-axis. If you like going the other way, and you have your function written this way, a times f of bx plus bc, and you don't want to factor out the b, then you shift first to take care of bc. Then you stretch by b. And then you stretch by a. We will see in a neat example later how these two work and how they produce the same answer. Here is one example with the table. Function f is given by a table, and we need to construct the function 2 times f of 3x plus 1. Let us do it step by step. So when we produce f of 3x, we are simply either slowing down or speeding up our function f. In particular, it will take the same values, 10, 14, 15, and 17, just not at the times where f does. When we multiply x by 3 inside of f, we're slowing f down 3 times. So in particular, instead of taking 6 seconds to get to 10, this new function will get 2 seconds. So we're not slowing down f, we're speeding up f. And we can check what is this function. Let's call it g for now. What is g of 2? Well, g of 2 is f at 3 times 2. That's f at 6, and that's 10. That corresponds to horizontal compression. Time compresses. By a factor of 3. Horizontal compression by a factor of 3. F is being sped up 3 times. So instead of taking 12 seconds, it'll now take only 4 seconds to get to 14, and instead of 18 seconds to get to 15, it'll take 6 seconds, and instead of 24 seconds to get to 17, it'll now get 8 seconds. That is f of 3x. The rest is very simple. All we need to do is multiply this by 2 to get to f of 3x. And to get to f of 3x plus 1, we simply add 1. And we can check one of them, for instance. Let's call this function temporarily h. Let's check that h of 6 is really 31. Well, h of 6 is 2 times f times 3, where instead of x I write 6. Outside plus 1. It's twice f at 18 plus 1. F at 18 is 15. And I get 31 as expected. Okay, let us now look at a graphical example. Use the graph of f given in the picture to sketch the graph of the function k, which is f at 1/2 x plus 3, and outside parentheses, negative 3. We will give two solutions to this problem, and both of them I'll show you on Desmos. You don't really need to know the algebraic expression for this function f. But we may pretend, even though the problem doesn't say so, we may pretend, for the sake of drawing these graphs on Desmos, that this is an upper semicircle centered at the origin of radius 2. The equation of the circle of radius 2 centered at the origin is x squared plus y squared equals 4. So from here, solving for y, you get y squared equals 4 minus x squared, and y is therefore plus minus root 4 minus x squared. Because we want the upper semicircle, we need the plus sign. So we pretend we know that this is the graph of the function positive root of 4 minus x squared. Although again, for simply making the picture on paper, it's not really necessary. So let us give two solutions. One will be the preferred way. One will be the solution where we first stretch and then shift. In my opinion, it's always easier. First stretch or compress, and then shift. So in order to write down that solution, we need to understand how we need to compress and shift. So I'd like to rewrite my function as f at 1/2 is taken outside, and in parentheses I have x plus 6. Outside the function I have negative 3. So now it's clear that we first horizontally stretch by a factor of 2. That will result in the graph of f of 1/2 x. Second step is a horizontal shift. We're going to be shifting by 6 units. Shift horizontally to the left. And our shifting to the left by 6 units will result in the graph of f of 1/2 times x plus 6. We replace x by x plus 6. And finally, step 3 in this first solution is a vertical shift. Downward by 3 units, and that will produce the graph of the desired function. All right, now the second solution. In this second solution, we will shifting first and then stretching. For this, I will use this form. So the first step is we shift horizontally to the left by 3 units. To obtain the graph of f of x plus 3. Now we stretch. Horizontally by a factor of 2 to produce the graph of f of 1/2 x plus 3. And you can clearly see that the first 2 steps result in the same picture. We'll see if that's really the case when we go to Desmos. And then step 3 is the same as in the previous solution, so I may just copy it and paste. So let us see how both solutions work step by step on Desmos. Again, we will, for that purpose, assume that we know, even though we don't, that the curve in the picture is the graph of 4 minus x squared. So here we are in Desmos, and here is the graph that we begin with, 4 minus x squared, square root. Now, when we produce the graph of f of 1/2 x, that'll stretch horizontally our function by a factor of 2, producing this blue graph. Now, when we add 6, rather when we replace x by x plus 6, that'll shift this blue graph 6 units to the left, producing this green graph. In particular, see the point 0, 2 shifted to the point -6, 2. Likewise, the point -2, 0 shifted to the point, -4, 0 shifted to the point -10, 0. And so on. And now this green graph we shift vertically downward by 3 units to produce this purple graph, which is the desired graph. So again, one more time. We start with the original graph in red. Stretch horizontally by a factor of 2, producing the blue graph. Now we shift horizontally by 6 units to the left, producing the green graph. And then the green graph is moved downward by 3 units, producing the purple graph. Now the second solution. We again start with the red graph, our original square root of 4x minus 4 minus x squared. And in the second solution, the first step in the second solution was to shift horizontally by 3 units, producing this black graph. The black graph is the red graph shifted to the left by 3 units. Now we're going to make a stretch. We're going to take the black graph and stretch it horizontally by a factor of 2. It'll be an interesting operation. This other red graph is the black graph stretched with a factor of 2. See, for example, that this implies also that we stretch the shift. The black graph was shifted by 1 unit from the origin. Whereas when we stretch the black graph, this shift of 1 unit also stretches, producing the graph shifted from the origin by 2 units. Also the peak in the black graph was away from the origin by 3 units. Now the peak in the stretch graph is away from the origin by 6 units. Then finally we take this second red graph and shift it downward by 3 units, producing the blue graph, which is the same as the purple graph in the first solution. So of course they are the same graph. You can now see why the first solution is, in a sense, easier than the second. In the second solution, we had to stretch a shifted graph, and it's usually more difficult than shift a stretched graph. So first, stretch and then shifting is easier. than first shifting then stretching, because you also have to stretch the shift. Right? The black graph is shifted to the left by 1 unit. When we stretch it by a factor of 2, we get a graph that is shifted by 2 units. Always keep that in mind. So I hope that was helpful, and this finishes the first topic, transformation of graphs, of week 3. Thank you.